We start off with flatbeds. Then, fault breaks to build up the wedge to the critical taper. New fault breaks to build the wedge to the critical taper. Because the detachment is tilted and sigma 3 is vertical, bisecting the angle between the forethrust and backthrust. Backthrusts exhibit steeper dips. Observe the backthrust and forethrust of fault 2 which just formed. Next, the first backthrust is too shallow. Material gets pushed into the backstop and can't build up the wedge. So material slips on the second backthrust instead. A new fault breaks forward each time the wedge reaches the critical taper. Let's observe a little more closely. We have an existing wedge starting to build up to the critical taper. It continues growing until the critical taper is reached at 7.12 degrees. Once reached, a new fault breaks so sediments getting pulled in can continue building the wedge. The wedge is no longer at the critical angle, and thus has to build up to 7.12 degrees again. Let's pause and make some observations again. Do you see what we see? Now observe how the faults tilt. From the diagram, we can tell that the angle of the backthrust becomes smaller as the wedge grows and the faults get tilted backwards. Similarly, the angles for the forethrusts change and become larger as the wedge grows and the faults tilt backwards. Fault 6 does not follow the same trend. Instead, its angle becomes smaller unlike the previous forethrusts. What's going on? At this point, there are no more sediments feeding in to build the critical taper. Therefore, sediments are pulled along the sandpaper at the bottom, causing the dip of the forethrusts to decrease. Sand falls back on itself due to gravity. Pretty cool, don't you think? But hold on. We're not quite done yet. Let's go a step further. Does the dip of the
décollement
affect the way fold and thrust belts form? Of course. For each line on the graph, the thickness of the original sand layers and sandpaper grits are kept constant. Across all experiments, we see a general trend where the steepness of the wedge increases as we increase the dip of the
décollement.
This agrees with the equation for critical taper wedge mechanics for dry sand, in which the steepness of the wedge, alpha plus beta, increases as beta, the dip of the detachment, increases. However, there are too little experiments, and we do not have enough points to accurately constrain the best fit lines. As a result, we were unable to obtain meaningful quantitative measurements to determine the basal friction, μb, and the value of internal strength, K, from the gradients and y-intercepts of the lines plotted. In future, it may be useful to conduct more experiments to better constrain the best fit lines, and then compare them with the theoretical model equations obtained by determining μ from analog experiments. Next, Does changing the thickness of the sand layers change anything? According to past research, the spacing between thrust faults decreases towards the foreland, where the sedimentary layers thin out. We tried to determine if this concept could be applied across different wedges with different original thicknesses. Here, we compared two sandboxes with the same dip of the detachment and sandpaper grit, but one of 5 cm thickness and the other of 3 cm thickness. Like what we would expect, we observed fewer and wider space faults in the thicker wedge. Again, if we had analog experiments to determine the coefficient of basal friction, we would perhaps be able to compare if changing the thickness of the sand layers affects K, the value of internal strength. The sandpaper popped up during the process of cranking. It may or may not have affected the way that faults formed. Our measurements were obtained from analyzing the photos on canvas. But the camera was not at the right angle and there was some degree of parallax error, making the measurements slightly inaccurate.